All right, so last week we finished up work and energy, okay? And then we went on to conservation of energy. This lab is going to look at both, okay? Work and energy. So there's one basically set of data to collect, okay, which is pretty straightforward. And then there are just a few questions that you need to answer after that. So I'm just going to open up your version of it here so that you guys see the same thing. My password's all little dots, in case you're trying to break in. Okay. Okay, so what we're looking at here, guys, is that we want to compare the amount of mechanical energy at the top of the ramp versus the bottom of the ramp. Okay, we're looking at a very simple mechanical energy conversion. That is, we're converting potential energy, gravitational potential energy, into kinetic energy by the time we get to the bottom of the ramp. All right? Everybody okay with that? Okay, so because this is happening in the real world, is the energy going to be conserved? Well, the energy is. The mechanical energy is not. Okay? We know that. We know that energy is going to be lost on the way down the ramp. So, as part of your observations, you might want to take like a quick video of the cart as it rolls down the ramp. You can then use that video to determine what other forms of energy are being produced by the cart as it converts potential energy into kinetic, because obviously it's not just converting it into kinetic, there are other things going on, okay, that will result in it having less kinetic energy at the bottom than it had potential energy at the top. Okay, so that's what we're investigating. It's a very simple mechanical energy conversion that you would be surprised is incredibly inefficient. Okay, all right. So when we're looking at this whole lab doesn't happen unless we put the cart where? Right. If we don't put it at the top of the ramp, there's nothing to start this lab. Okay? So since we're comparing the gravitational potential energy of the cart at the top to the kinetic energy at the bottom, okay, we're looking at our two kind of important variables there. Okay? We're doing something to give that cart its initial gravitational potential energy. Okay? And then we're comparing its kinetic energy at the bottom. Okay? Its kinetic energy at the bottom is dependent or responds to the amount of gravitational potential energy that it was manipulated to have earlier. Some of you got that. Good. Okay. Now, because this whole lab is being performed on Earth, there is one important variable that will remain controlled, not actively by you, but because the Earth's mass does not change considerably during the experiment, hopefully, okay, this thing will remain the same. Okay, kind of important because it's part of the potential energy formula, and we kind of need it to stay the same. Okay, we are going to run 3 trials, but we're not comparing the 3. We just want to have 3 trials so we can get a good average. Okay, so I don't want you to think that we're doing anything with the 3 trials other than just averaging them together, okay, for the sake of accuracy. Other things that could alter this experiment, okay, when the cart is traveling down the ramp, we need to think of other things that need to stay the same as the cart travels down the ramp that could affect the difference between the energy at the top and the energy at the bottom. Okay, so when you're thinking of controlled variables, think of anything else that needs to stay the same as the cart travels from top to bottom. Okay, for your hypothesis, okay, we got our if, and then statement. The if part, not in the right thing. Okay, the if part should talk about the law of conservation of energy. Basically, it just needs to tell me what the law of conservation of energy says. Okay, if the law of conservation of energy, blah, 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 okay? Okay, the and part, as always, describes the experiment. The mechanical energy of a cart at the top of a ramp and the bottom of a ramp are compared, like that. Okay, then, the then part's going to be a bit longer. Okay, you have a choice in your then part. You can make your then part as though this experiment is operating in the perfect physical world. Okay, now if you say that, obviously your data will not support your hypothesis, and that's okay as long as you say so in the conclusion. All right, or you can talk about the then part as though it's going to happen in the real world, which is of course where we are actually carrying out the experiment, and then your hypothesis will likely be supported. But the then part needs to tell me what this is going to look like. Is the kinetic energy at the bottom going to equal the potential energy at the top? Why or why not? Okay, so if you're choosing to do your hypothesis as though this is in the real world, you tell me why. Okay, if you're telling me this is in the perfect world, okay, if you're doing this for the real world, then you need to tell me why not. Okay, because obviously you're going to say no, they're not going to be the same, and you need to come up with the culprits. Okay, now if you make your hypothesis and say that they're going to be equal, that's the perfect physical world, then in your conclusion you have to explain to me why they weren't. Okay, so you're going to have the same reasoning, it's just where you put it. You're either going to put it initially in your hypothesis, or you're going to talk about it later in your conclusion. Okay, it doesn't matter. Okay, questions so far? All right, the experiment is really, really easy. Okay, you're going to put the cart at the top of the ramp, and you're going to start your spark view recorder, and you're going to record its travel to the bottom of the ramp. Okay, stop the cart at the bottom of the ramp. Everybody with me there? Okay, it's really important that we stop the cart. Don't let it go off the bottom of the ramp. Okay, it's really hard on them to do that. So stop it at the bottom. Then all you're looking at is the maximum speed of the cart. Okay, because that can be used to calculate your what? Your kinetic energy at the bottom. Okay, whatever that maximum speed is. So just looking at your chart, you only need the one column from your chart because it's going to spit out all that crap it always spits out. You just need the velocity column. Whatever the maximum speed is, that's the number you need from your data. Okay, so you're not going to have to build a graph or anything like that. You just need to look through the data for the biggest number for each trial for velocity, and you're set. Okay. All right, so to calculate the potential energy, you're going to need the mass of the cart, which is here in your chart, your observations chart. Okay, you're going to need the speed of the cart at the bottom of the ramp, greatest values recorded by SparkView, height of the cart's center measured from the floor. So when you set this up, okay, and you're going to have it set up like this, you're going to take a meter stick and you're going to measure not to the ramp, but to the center of the cart's height. So not to the top of the cart, but to the center of the cart, because this is all done as though it's to the center of mass. Okay, that will be your height for calculating your potential energy. That height should be around 15 centimeters. Okay, make your ramp so it's around 15. If it's more than 20, it doesn't collect a lot of really good data because it goes too fast. Okay. All right, and then the length of the ramp. Okay, which we need to calculate something later. So just measure the ramp. Okay, take out the meter stick and give the ramp a measure. Okay, cart's mass, okay, which we have there. Okay, all right, so that's all you have to do for data gathering. Okay, you have to measure three things: height of the cart, which is going to stay the same every single time. Okay, the length of the ramp, same every single time, and the maximum speed of the cart, which is going to be really close, but you're going to get three different values there. Okay, you're going to record all of that in the chart and average it. Obviously for the height, that's easy because it'll be whatever this number is down here. Okay, for the speed, put the three values in, add them together, divide by 3 to get your average. Okay? And then you're going to perform the calculations here in the analysis. So show me your calculation of potential energy. Show me your calculation of kinetic energy, okay, using the average value. Okay? And then talk in number 3, were they equal? Why or why not? Suggest reasons. Okay? And then for number 4, this is where the length of the ramp comes into play. Okay? Friction does all the work in slowing the cart, or it represents basically where the energy is lost. Okay? I want you to calculate the coefficient of friction between the cart's wheels and bearings. Now, you will need theta for that. Okay? But you'll be able to calculate theta because this will be your height and this is the length. You will have measured both of those numbers, so you'll be able to calculate theta and get your normal force and all of that. Okay? And that gives you a little extra practice on inclined planes before your test on that. Okay, number 5, what can this lab tell us about the efficiency of mechanical energy conversions? That's just something for you to think about and then write something about. Okay, are they efficient? Are they not? Does that have implications? Okay, what are some ways to increase the efficiency of that conversion? Okay, just come up with a few ideas as to how could you make more of the potential energy become kinetic as the cart goes down the ramp. For your conclusion, okay, copy paste your hypothesis, tell me whether you can accept or reject it, and then any sources of error that you can think of and ways to fix them, same as always. All right, questions on what we're doing? Okay, so make sure you do this on the floor. Okay, put your ramp on the floor. A couple of binders is probably all you need to build up the height of the ramp. Okay, carts are here, so grab a ramp and a cart, and you're good to go. Okay, if anybody has any questions or needs any help, just let me know.